Hi, I'm Adrien. I'm a researcher at Imperial College London, and I work on brain-machine interfaces. Or at least that's generally how I introduce myself. I'm actually an electronic engineer. Shy creatures, I know. The most annoying thing for an engineer is a machine that doesn't work. The next most annoying thing is a machine that works, but nobody really knows why or how. And that's the brain. The brain's pretty amazing. It has 86 billion neurons, and between them, 500 trillion connections in the average adult. It runs on about 20 watts, or the same as this light bulb. It does so without you having to think about walking or talking at the same time, and all of those functions are integrated in an organ about the size of this grapefruit. The brain confounds us, and when it stops working, we don't really know why. People start forgetting things, or they see and feel things that aren't there in reality. Or they lose control of their limbs. And generally, when the brain stops working, it's pretty bad. Now, when you break your leg, a doctor will set your bones correctly, and you'll get a cast, and you'll be walking in crutches for a while, but at the end of it all, you'll walk straight again. It's almost guaranteed that you'll heal. But when you break your brain, that's another story. Nobody knows whether you'll recover for sure. And we have drugs that we can use to shove the brain in one direction or another as part of therapy. But we also have devices that we can implant inside the brain in order to stimulate and record from it in order to understand what's going on and to provide some other forms of therapy. These devices are called brain-machine interfaces. Some of these technologies are still quite crude, and yet they still work. Some of them amazingly so. Take cochlear implants, for example. These are devices that can restore your hearing when you are born deaf or when you become deaf. There are 20,000 cochlear implant users in the UK alone, and about 1/3 of them are children. They work by stimulating a very specific part of the nervous system inside your ear, directly connected to the brain. We can do that because we understand very well how the inner ear works. However, that's not the case with most of the rest of the brain. But things are changing. You might have heard in the news about companies like Kernel, Neuralink, or Paradromics promise you things like being more aware of your emotions or your inner state of mind, and warning you when you're distracted during dangerous activities like driving. Or even control a robot arm with nothing but your mind. But we already knew how to do that 10 or 20 years ago. If we look at the BrainGate project, back in 2006, they were showing us already how a patient without the use of their limbs could move a computer cursor around, open emails, and surf the internet. But perhaps a more well-known video is one they published in 2012, showing a woman, a tetraplegic, controlling a robotic arm in order to pick up a bottle on the table and drink, unaided. Think about the implications for someone who, at the time of the video, hadn't been able to move her legs for 15 years. You'll notice in both these examples there were embedded connectors in the patient's skull. The difference with newer interfaces is that they're now small enough to be completely implantable. They're invisible, just like cochlear implants. And you don't have to wait hours to start a recording, calibrating your device. You don't have antennas sticking out of your hair. Companies hope that this will make these technologies more acceptable to those who would benefit from them. For example, paraplegics and tetraplegics, or patients with ALS, conditions that prevent you from using your muscles correctly. For example, you could control an exoskeleton to hold you upright, and it would be like an extension of your will. But there's something else. We are no longer in a research context. These devices are geared towards the general public. We're entering a phase where brain-machine interfaces are no longer just in the lab, no longer just for therapy. What if I were to tell you today that tomorrow you could get an implant for work, to do remotely what would have required you to be there previously? For example, to communicate thoughts, feelings, and emotions, and the subtleties of language that are very difficult to translate into text or even into FaceTime video. That sounds a little bit like a phone, doesn't it? And what is a phone but a device that translates your voice into code and back again for the receiver at the other end? Now, our phones today do much more than that, of course. We use them not only to call, but also to look up videos and funny memes and pictures of cats on the internet. And we keep them on us most of the time. As a matter of fact, people get quite uncomfortable without their phone once they've become used to having it. It's become a universal prosthetic for something that we were never born with, our gateway, so to speak, to the internet. What if it could be the same with an implant? The question is one of information. The amount of information that you can transfer in one communication. They say that a picture is 1,000 words, but how many words would it take to express complex thought? Here, I've been speaking to you about one idea for about 5 minutes. But if we knew how to translate that idea into code and back again, it would take me just a moment to express the same thing. And that's the key difference with brain-machine interfaces. So where do we stand on doing that currently? A typical application, or rather a traditional application, for brain-machine interfaces has been motor control. This is to restore function to limbs that you've lost through injury or amputation. And after decades of work, we can get a pretty reasonable idea of what you want to do based on the signals coming from your motor cortex. This is the region of the brain currently targeted by Neuralink for implantation. In their latest showcase video, Neuralink shows us a monkey driving a cursor around a screen using a joystick. They're recording signals from the monkey's brain while it's doing this task, and then they leave the joystick unplugged. Yet we can still see the cursor moving through the correct locations on the screen. So how does that work? They look for the same signals that emerge when the monkey is moving the joystick as when it was plugged and when it was unplugged. The signals don't change. They allow us to interpret where the monkey wants to move the joystick and therefore where the monkey wants to move the cursor, with potential applications for paraplegics and tetraplegics. The difference here is that, contrary to previous experiments, there is no port on the monkey's head. The implant is essentially invisible. And this has important implications, not least of which one of acceptability for any user of this technology, but also to reduce surgical risk. One day, getting such an implant could be routine. However, that's all well and good, but for people with healthy arms and legs, motor control implants aren't particularly useful. We can get around just fine, and we can pilot machines with a joystick, for example. What could be far more useful to us is the ability to express our feelings and emotions through our brain implants, but that is a far more difficult task. Think about how we could code emotions and communicate them reliably, effectively. Emotions exist on a spectrum. When we think of emotions, we think of happiness, sadness, fear, anger, frustration, joy, and unease or disgust. There are so many different emotions, and it's very difficult to effectively communicate them unless we're face-to-face. There are a lot of nonverbal components. For example, if we use a phone to communicate emotions, generally we use emoticons. However, think about how many times you were confused by somebody else's use of emoticons. There's basically no established code. But perhaps you'll find that reassuring. There's no doubt that some people will find the idea of brain-machine interfaces invasive. What if I were spied on? Or how could this technology be used against me? For example, could I be controlled by my own implant? These are all valid and important questions. There are some things that we can tell about the brain activity, your brain activity today. For example, if you're concentrating on something or not. And it's been reported that by looking at activity in specific parts of the brain, we can tell whether you're lying. But that would be an exaggeration. The brain never gives quite the same signals when thinking about the same thing. That's a process we call stochastic behavior, and it makes interpretation of complex concepts, like feelings and ideas, extraordinarily difficult. However, as with all technologies, brain implants have the potential to be abused. Just like our phones. Think about how much your phone knows about you, where you are, what you are doing, and how, when hacked into, so many things can be told about you. Well, the same thing could be applied to brain-machine interfaces. Fortunately, we are having this conversation right now about what the risks could be. And governments are already looking about how to regulate these technologies to reduce risks for their users. It is particularly important right now to have this discussion, ethical discussions, around the safety and use of brain interfaces before they enter widespread use. And one last thing. When you take a step back, brain interfaces have always been about translation, translating signals to and from the brain in order to restore old communication pathways or enable new ones. Think about the impact that this technology could have on us in the future. Our ability to communicate remotely to each other using feelings and emotions that are out of reach for our phones. To do that, would you connect your mind to the internet? Thanks for watching.